Hi, it's time for another math easy solution. Here to discuss further into interpretation of the derivative as a rate of change. Now look at example 2 of this video series. You can see the earlier videos in the video links below on this. But basically this example states, this was a useful one in my calculus book, and it states right here, let D of t be the US national debt, i.e., well, national debt is just money borrowed through various means. I'm not going to go too much into it. And this is, let's say, let D of t be national debt at time t, and the table below this one here gives approximate values of this function by providing end of the year estimates in billions of dollars from 1980 all the way to the year 2000. And now the question states, interpret and estimate the value of the derivative of this d function, the debt function, at 1990 right here, and what does it mean? Now, like I stated in the interpretation of rate of change video in the video link below, basically it states the derivative at, well, in this case you could write it as derivative at 1990 just means that the rate of change of d or debt with respect to time when the time is 1990, or in other words, basically the rate of increase of the national debt in 1990 right here. And when we interpret the derivative as a rate of change, you could write this one as this one right here using the definition derivative, but in terms of rate of change, as limit as t approaches 1990 of this one would be d of t minus d of 1990 all divided by t minus 1990. And this is the same meaning as limit as delta t approaches 0 of delta d over delta t. And as you can see here, the bottom is going approaching 0 right here, and then the delta t is just the top, is just well, the difference between d of t and d of 1990 right here. Now, if we were to estimate a value for this, so we've gone over interpreting what it is basically rate of change. Now, if we were to estimate this value, what it is actually, we could estimate by using the average slope. I'll just write s at any given point compared to the 1990 as d of t minus d of 1990. So instead of the limit as it approaches basically 1990, we'll just have it like this. We'll just have the difference and then see and make a table of it and see what happens. I'll show you what I mean. Alright, so here I've made actually an Excel sheet, and you can also download this in the video links below. And basically I have the same table here, and I've graphed this at 1990. So remember, the rate of change or a D19 or the derivative at here is basically the tangent line to it. So it would be something like this. So we are basically trying to estimate this slope right here, or D of derivative of 1990. And now if we were to do that average slope from every one of these values, so right here I've made a column with this average slope right here, and I've had it in basically just the top part, this d of t, which is right here, of 1980 minus this one 3233, which is d of depth at 1990, etc. minus then the 1980 minus 1990. And I've got it going on for every column and every row except this one here. That's just 1990. You're gonna have either divided by 0, so you can't really find out what it is. And as you can see here, so what this means is that, well, from here to here, if we go from 1980 all the way to this point, if we were to draw a line, let's change the color to, let's say, blue. So from here to here, actually I made it green. So basically from here to here we have 230. If we were to go from 1985 to here, we get basically 257 is the 257 is the slope. And then from here to here, which is going to be a bit higher, this one is from 1990 to 1995. That's 348. So as you can see, it's higher. Let's erase those. So it's basically the slope is higher from here to here versus here to here. So basically this d of 1990 should be somewhere in between right here. So we could just have to estimate that slope. And one quick way of doing that is if we take these two, so it should be in between these because it's high up here and it's lower on the bottom. And since it's smooth line like this, then basically it should be, we can just estimate it as the average of these two numbers. And we could just write average, and then we can go this number, hold control, and this number, or just comma that, and it'll be 302. Yeah, so 302, or we could round it up to 303 basically billion dollars per year. So that would be the derivative of it, and it means that it's basically increasing at this point at roughly $300 billion per year. So probably at 1990 you could even make the estimate that the national debt increased by $300 billion. And I'll just write that down here basically. From the Excel file, the derivative of the debt function at 1990 is around $303 billion per year. Well, anyways, that's all for today. Hopefully you learned from this quick example on how we could basically use the interpretation of the derivative as rate of change to solve word problems like this. And remember, you can also download these notes as well as the Excel file in the Dropbox links below. And that's all for today, and stay tuned for another math easy solution.